Hello everyone and welcome to today's webinar about maximizing RFID system performance under varying conditions. My name is Amin. I am RF Application Engineer at EMWorks. This is a brief overview of the presentation. So first we'll be talking about the RFID working principles as well as the application of RFID and some of the key differences between the RFID and the barcode. Following that, design challenges and some of the simulation results will be presented. At the end we have a live demo. So in case if you have any question, I'll be happy to answer them at the end of the presentation. Alright, so let's talk about the working principle of the RFID system. What does it mean, RFID system? RFID system simply is a technology that uses the RF signal for the automatic identification of objects or persons. RFID system composed of several components. These include a reader, antennas, tag, and subsystem for data processing. On the right hand side we can see an image of an RFID system. So basically the reader is transmitting electromagnetic wave and then the tag receives this electromagnetic wave and then responds back by sending the information that is stored in the memory of the chip. When the tag receives the electromagnetic wave, it develops an RF voltage at the terminal of the tag antenna. The voltage is then converted to DC voltage to turn on the chip. For the RFID system, basically there is like two working principles. First is called the electromagnetic far field electromagnetic coupling, and the second working principle is the inductive coupling, and this is based on the near field. Alright, so let's talk about some types of the RFID. RFID systems are classified based on the power source of the tag and the frequency of operation. For the power source, we have a passive tag which is powered by the reader, and the active tag which is powered by the battery. Also we have what we call the semi-passive. So for the semi-passive, so for the communication from the tag to the reader, it uses a battery. For the frequency of operation, we have mainly for frequency bands. So we have the low frequency, high frequency, ultra high frequency, and the microwave frequency. But today we'll be focusing on the ultra or UHF RFID system. Alright, so let's talk about UHF RFID. UHF RFID has gained popularity in the last few years due to several factors. First, RFID has a long read range. It can go up to 10 meters. It also has a high data throughput and fast anti-collision. For instance, the RFID reader can scan more than 100 tags at a time. The tags can be easily embedded into solid non-metallic objects. For the RFID tags are mostly printed, so they are easy to manufacture and are less expensive. One of the drawbacks of the UHF RFID is the poor performance when there is liquids or metals in the surroundings. Alright, so let's talk about some applications of the RFID. RFID, it's used in several areas. So for example, it can be used for the inventory management, personal and animal tracking, as well as controlling access to restricted areas. It can also be used for counterfeit prevention or contactless payments such as credit cards. Here are some few images showing some application of the RFID, such as the access to restricted areas, contactless payment, and as well as the animal tracking. Alright, so let's talk about some key differences of the RFID and the barcode. Barcode, RFID, it has one of the major advantage of RFID is that it can scan multiple of tags at single time. It has a faster read speed Tracking the tags for the RFID doesn't need a line of sight, as is the case in the barcode. For the barcode, it's read only, so basically we can only read the information from the barcode, so we cannot edit or write any information on the barcode, which is not the case in RFID. So for example, for the RFID, we can both read and write. Alright, so now let's talk about some design challenges of UHF RFID. There are several factors that degrade the RFID performance, mainly the read range. And these include the impedance matching between the tag antenna and the chip, also the sensitivity to some objects such as the liquids and metals, as well as the dielectric materials. The read range is also affected by the transmitted power of the reader and also the sensitivity of the chip. The read range is also affected both by the gain of the reader and also the gain of the tag. This is the RFID system. Alright, so now let's talk about the RFID system. This is UHF reader antenna, and this UHF, it has segmented loop antenna on both sides of the substrate. The substrate is made of Rogers 5850 with permittivity 2.2 and loss tangent of 0.009. So for the reader, so it has a segmented loop antenna, and inside the segmented loop antenna there is the patch. So the reason for this is for the segmented loop, it's used for the near field communication, and for the patch it's used for the far field communication. So basically now we have two types of communication, both the near field and the far field. The antenna is considered as electrically large and has a length of almost lambda over 2. So now let's talk about the tag antenna. So for the tag antenna, it's modified Minder structure with the semicircular feeding network. At the terminal of the feeding network, we have the IC chip. The IC chip has impedance of 25-J-37 at frequency of 862 megahertz. The sensitivity of the chip is -18 dBm, which is equivalent to -48 dBW. On the right hand side, we can see a picture of the tag antenna, which is attached on a bottle. Alright, so let's discuss some of the simulation results. On the right hand side, we have the return loss for both the reader and the tag antenna. Both the reader and the tag antenna resonate at the same frequency of 868 megahertz. On the left hand side, we can see an animation of the electric field around the reader and the tag antennas. In HFX, we can see the 3D gain pattern of the antenna. So, for example, on the right hand side, we have the 3D gain pattern of the tag antenna, which has a gain of 4 dB. So you can see the omnidirectional pattern. On the left hand side, we have the 3D gain pattern of the reader, and it has directivity of 9 dB, and it's directional, and it has a directional pattern. In the middle, we have the 2D gain pattern of both the reader and the tag. So from the 2D pattern, we can clearly see that the tag antenna has omnidirectional, while the reader has directional pattern. In HFX, we have what we call the results table. And the results table, we can see different antenna parameters, such as the maximum gain, radiation efficiency, and the total efficiency. So in our example, the reader antenna has gain of 9 dB and total efficiency of 84%. As for the tag, it has a gain of 4 dB and total efficiency of 60%. Alright, so now let's talk about the effect of dielectric and metal on UHF RFID. On the right hand side, we have the return loss for the tag antenna, which is attached on different objects. So for this, we want to study the effects of the glass, the plastic, and the metal. From this plot, we can clearly see that the dielectric material causes detuning of the resonance frequency. As for the metal, so first it causes a detuning of the resonance frequency. It also has an impact on the impedance mismatch between the also it causes a big impedance mismatch between the tag antenna and the chip. On the right hand side, we have the insertion loss for the tag antennas on the different objects. From this plot, we can clearly see that the metal has a big effect in the power received by the tag antenna, and this is due to the detuning as well as the impedance mismatch. But still the tag antenna is still, it can still turn on the chip. It has received almost minus 40 dB, which is enough power to turn on the chip. Alright, now let's look at the some of the far field results table for the metal. Previously, we have seen that the tag antenna had a gain of 4 dB and total efficiency of 60%. When we mount the antenna on a metal bottle, so we can clearly see that it has effect on the accepted power due to the impedance mismatch, and also it has effect on the radiated power, as you can see from the total efficiency, and this is due to the metal. So basically now the metal is in the nearby of the tag antenna, is blocking, so is reflecting part of the radiation. It also creating destructive interference for the radiation. Alright, so let's talk about the liquid effect for the RFID system. RFID system, one of the challenges for the UHF RFID system is the absorption from the liquids. So to study the effect of the liquids on the performance of our antenna, so basically we put a bottle in between the tag, which is mounted, which is in free space, and now we wanted to study the effect of the liquid. So for this, we put the orange juice inside the middle bottle in a metallic bottle. On the left hand side, we can see that you can clearly see that both the liquid and the metal has effect on the insertion loss. So we can see now the received power from the intake is significantly reduced due to the absorption from the liquid, but still the received antenna, the tag antenna, still received enough power, which is sufficient to turn on the chip. So we can see that our antenna is still functioning even when it's placed near liquids. Now let's look at the range of the antenna for the different under different environmental conditions. Through the use of parameterization, we find the read range for the antenna in free space. So on the right hand side, we can see that for the tag antenna, it has a read range of 2.5 meter. So by looking at the read range, by looking at the plot on the left hand side, we can see that the antenna on plastic has a read range of 2 meter, while the antenna attached on the metal has a read range of 1 meter. When there is a liquid in the nearby, the read range of the antenna gets reduced almost to 1 meter. Now we have a live demo. We'll be showing you how to simulate such system using UHF Works. This is UHF Works and this is SolidWorks. UHF Works is fully embedded in SolidWorks and is called certified by SolidWorks. In UHF Works we have 4 types of study. We have antennas, S-parameter, TDR and resonance, but today we'll be focusing on antennas. For each study we have mainly 3 steps. So first we need to specify the level of accuracy, the frequency range, as well as the meshing. So if you know how to do the mesh, you can use manual mesh, otherwise you can use adaptive mesh. Next we need to apply material. So to apply material, so you right click, we say apply material. In UHF Works we have material library, so we have different material from different vendors. Once we apply material, the next step is to set up the boundary condition. For boundary condition, we have different boundary conditions. We have port, lumped element, PEC, PMC, PEC symmetry, PMC. We have radiation, boundary, and signal. So if you know how to, if you decide to go for the manual mesh, you can use the mesh control to apply mesh control. So for mesh control, so you can apply mesh control on bodies, faces, edges. You can also specify the element size. Alright, so let's look at the our RFID system. So for this system, so basically now we have the bottle, and now the tag antenna is mounted on the bottle, and this is the reader antenna. So for this bottle, so we change in our case, so we put the material for this air. So this, as there is no obstacle between the bottle and the reader antenna. So for this, and for the chip, so here for the chip, so for the IC chip we use what we call the lumped port. So we said the edit definition. So for the lumped port, so we have a parallel, so it has a resistance of 25 and the capacitance of 0.77 picofarad. So let's look at some of the simulation results. In UHF Works you have what we call the results table. And the results table we can see different circuit parameters such as generalized ACE matrix, renormalized ACE matrix, impedance matrix, port results, VSWR. We can export results versus current frequency or all frequencies. So we can export results to different formats such as text file, CIT, SPC, or touchstone. We can also print results. So let's look at first at the return loss of the reader and the gain of the tag antenna. So from this plot we can see both the tag and the reader have almost resonate at the same frequency, which is 868 megahertz. So let's look at the effect of the dielectric and the metal. So initially the antenna was resonating at a frequency of 868 megahertz, and because of the dielectric, so now there is a shift in terms of the resonance frequency. As for the metal, it creates both two effects. It detunes the resonance frequency, and also it causes impedance mismatch between the tag and the chip. Because of the detuning effect and also the impedance mismatch, we can see now the power received by the tag is reduced. The metal has the biggest effect in terms of the received power, but still the tag antenna received enough power, which is minus 40 dB watt, which is enough to turn on the chip. So we can see from this plot that our antenna is still performing even when it is mounted on the plastic or is mounted on metal. So let's look at the also in UHF we have what we call the antenna far field results table. Under antenna results far field table, we can see different antenna parameters such as the gain, the radiation efficiency, and the total efficiency. We can again export or print. So let's look at the gain of the reader antenna. So here we can see, so from this plot we can see the antenna has direction pattern with a gain of 9 dB. As for the tag, it has omnidirection pattern of a gain of 4 dB. We can even plot to the radiation pattern for the reader and the tag. Again, we can see the tag has omnidirection pattern while the reader has directional pattern. In UHF also we can do what we call the section plot or section animation. So for this we need first to show the error. So we can right click, we said animate versus phase. So maybe we can zoom a bit. So now we can see the electric field animation around the reader and as well as the tag. So let's look at the animation of the electric field for the reader and the tag. In this case we need to hide the air. So first the tag is turned on and the reader is turned off. So now we can clearly see the electric field animation. This time the reader is on but the tag is off. So to animate, again we right click, set animate versus phase. So we can zoom a bit. So you can clearly see the animation of the electric field. Alright, so let's look at the effect of the metal. So in this case, so here, so the tag is mounted on stainless steel bottle, and for the bottle in between it's air. So now we're studying the effect of the metal. So first let's check the return loss. So from this plot we can clearly see there is for the metal there is two effects. First there is detuning effect, and also there is an impact on the impedance mismatch between the tag antenna and the chip. The detuning and the mismatch effect creates the reduction in the causes the reduction of the received power by the tag antenna. The received power for the tag antenna at a distance of 0.5 meter is minus 40 dB watt, which is still enough to turn on the chip. So let's look at the effect of the liquid. So now we're trying to see what happened to our antenna when there is a liquid in between. So for this, so again, we have now tag antenna, and the liquid, and this bottle now is filled with orange juice. And this orange juice, also we want to study two effects, the liquid and also the metal effect. So for this we applied stainless steel. We applied imperfect electric boundary condition. So first let's check the return loss. As expected, so there is no big difference in terms of the return loss, but the effect is in the insertion loss. So we can clearly see there is the attenuation of the power, and this is due to the absorption of the electromagnetic wave from the liquid, which is in our case the orange juice. Alright, so now let's see how we can find the read range using UHF Works. So in UHF Works, so again this is our model. So now we want to find read range for the RFID, for the tag antenna. So through the parameterization, with parameterization we can see the effect of different parameters on the system performance. So in our case, we wanted to study, we wanted to find out the read range of the tag antenna. So for this we apply the parameterization. By using parameterization, so now we can find the power received at different distances. So in free space, the optimum distance for the read range is 2.5. At distance we have almost 46 dB watt, and this is just enough to turn on the chip. So let's look at the effect of let's look at the read range and the different conditions. So again we apply the parameterization. Alright, so through parameterization study, so we can find out that the read range for the tag on a plastic is 2 meters, while the read range for tag on metal is 1 meter. When there is a liquid in the surrounding, the read range of the antenna gets reduced from 2.5 meter to almost 1 meter. Alright, this is come the end of the live demo. Now to summarize, you have learned the effect of dielectric, metal and the liquids on the performance of UHF RFID. The dielectric and the metal cause detuning of the resonance frequency, while liquids reduce the amount of the energy received due to absorption. This effect can reduce the read range of the tag, or can even make the tag not read at all. We have demonstrated you how UHF Works can help us design robust UHF RFID system that maintains a good performance in the vicinity of metals, liquids, and dielectric materials. With that, I would like to thank you, and now the floor is open for questions. Thanks.